Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to online lecture. Today our topic is VSPR theory. Dear students, this topic consists of introduction of VSPR theory, main points of VSPR theory, and applications with structures of molecule of VSPR theory. First of all, we should know about the introduction of VSPR theory. VSPR stands for valence shell electron pair repulsion. Dear students, this theory was pointed out by two scientists, that is Sedgwick and Powell, in 1940, but explained by two other scientists, that is Newholm and Gillespie, in 1957, in order to explain the shapes of molecule for non-transition elements. So this theory successfully explains the shapes or geometry of molecules. Now, main points of valence shell electron pair repulsion theory. The first point is both bonded and lone pairs of electrons determine the geometry of molecule. Second step is these pairs arrange themselves around the central atom to have maximum distance and minimum repulsion. Third point, the lone pairs of electrons occupy more space than the bond pairs. It is due to that the lone pair of electrons are under the influence of only one nucleus. So these pairs of electrons are high energetic, that's why these occupy more space. But the bond pairs are under the influence of two bonded nuclei, so these pairs are lower in energy, that's why these pairs occupy less space. Fourth point, the repulsion order between the electrons pair is as lone pair repulsion is greater than the lone pair bond pair repulsion, which is greater than the bond pair repulsion. Fifth point, if all pairs of electrons are in bonding, then shapes of molecule will be regular. If there is one or more than one lone pair of electrons present with the central atom of molecule, so that molecule will have irregular structure. The overall geometry of the molecule depends on the number of electron pairs and the valence shell of central atom. So deviation from the expected bond angle is due to presence of lone pair of electron. Now, applications of VSPR theory. First of all, shapes of molecule containing two electron pairs. For example, beryllium dichloride. So beryllium is the central atom of this molecule. So the electronic configuration of beryllium shows that beryllium has two electrons and the valence shell, so it can form two covalent bonds with two chlorine atoms. As the structure shows that there is no lone pair of electron with the central atom, that is beryllium, so it will have a regular structure which is linear in shape, so the bond angle will be 180 degree. It is due to obtain the maximum distance and minimum repulsion. Now, shapes of molecule containing three electron pairs. For this, the first example is boron trifluoride. Boron is the central atom of this molecule, so the electronic configuration of boron shows that there is three partially filled atomic orbitals present in the excited state of boron, so it can form three covalent bonds with three fluorine atoms. These three bonds pairs are situated at equal distance from each other to have maximum distance and minimum repulsion. The bond angle is 120. Therefore, boron trifluoride has triangular planar structure, which is a regular structure. This structure is also regular due to the absence of lone pair of electron with the boron. Now, second example for this kind of molecule is stannous dichloride. The central atom of this molecule is stannous, so electronic configuration shows that there is 4 electrons present in the valence shell. Two electrons present in s orbitals which remains non-bonding due to the inner pair effect, and two electrons of p orbitals form two covalent bonds with two chlorine atoms. The non-bonding electrons behave as lone pair occupy more space than the bond pairs. Hence, the expected geometry triangular planar changes to angular structure, and bond angle also decreases from 120, which is approximately equal to 95 degree. So as the structure shows that there is one lone pair of electron present with the central atom. So the lone pair of electron is under the influence of only central atom nucleus, so it is high energetic and will occupy more space, so it pushes the bond pairs which is lower in energy at one side, and the regular structure convert into irregular structure that is angular, and the bond angle also decreases. Now shapes of molecule containing 4 electron pairs. For these molecules, the first example is methane molecule CH4. The carbon is the central atom of this molecule. So the electronic configuration of carbon at excited state shows that there is 4 partially filled atomic orbitals present. So it means that carbon can form 4 covalent bonds with 4 hydrogen atoms. So there is no lone pair of electrons, hence the geometry is regular, that is tetrahedral. According to VSEPR theory, all bonded pairs of electrons are situated at equal distance from each other to have maximum distance and minimum repulsion, and the bond angle is 109.5 degree. As the structure shows that carbon has no lone pair of electron, there is four pairs of electron which are in bonding. There is no lone pair of electrons, so its geometry will be regular, which is tetrahedral, and the bond angle will be regular, which is 109.5 degree. Now second example for this molecule is ammonia. Nitrogen is the central atom of ammonia. So the electronic configuration of nitrogen shows that there is 3 partially filled atomic orbitals present in the nitrogen atom. Electrons of 2s orbital remains non-bonding, and 3 electrons of p orbital form 3 covalent bonds with 3 hydrogen atoms. So according to valence shell electron pair repulsion theory, lone pair bond pair repulsion is greater than the bond pair repulsion. Hence, lone pair pushes the 3 nitrogen hydrogen bonds, which decrease the bond angle from 109.5 degree to 107.5 degree. And the geometry also changes from tetrahedral to triangular pyramidal structure. So look at the structure of ammonia. Nitrogen is the central atom. There is total 4 pairs of electron, in which one is non-bonding. So this is high energetic and occupies more space, and that's why so it pushes the other bond pairs electron at one side, and the regular structure changes into irregular structure, that is pyramidal, triangular pyramidal structure, and the bond angle also changes from 109.5 to 107.5 degree. Now the last example for this kind of molecule is water. Oxygen is the central atom of water molecule. So the electronic configuration shows that there is 2 partially filled atomic orbital present in the center atom. Oxygen contains 2 bond pairs and 2 lone pairs of electron. According to the valence shell VSEPR theory, lone pair repulsion is greater than the lone pair bond pair repulsion. The 2 lone pairs of electron push more the oxygen hydrogen bonds pair, and the bond angle decreases from 107.5 degree to 104.5 degree, and the geometry changes further to angular structure or V shape. as the structure shows that the central atom has total 4 pairs of electron. Among these pairs of electron, 2 are in bonding and 2 pairs are non-bonding. So the non-bonding pairs electron are high energetic, so these occupies more space and pushes the low energetic bonding pair at one side, and the geometry changes to angular structure and the bond angle changes decreases to 104.5 degree. So these are the structure of water molecule. So this is the water molecule structure, which shows the polarity of water molecule by the dipole moment. So dear students, if this video is fruitful for you, so like and share it and subscribe my YouTube channel. Thank you.